Hello, everybody. In this live, what we're going to do is continue with where we left off last time. Remember, this week the key topic we've been going over every day has been the derivative, or sorry, not the derivative rules, the integral rules. We talked about how to do the integral of polynomials, trig functions, exponentials, and logarithms, kind of for logarithms, as much as we can at this point, anyway. And now what we're going to do is we're just going to continue going over the integral rules, but we're going to go over one technique I'll say that's called U-substitution. So this is a common technique you'll deal with in AB, AB and BC. This shows up, but here let me actually start my screen share. So there we go. So yeah, and also if you have any questions, during the chat, feel free to just drop them in the chat, and I'll answer them as I see them. But otherwise, we'll just kind of dive into the topic I had planned. So basically, with this, what will I say? Or how should I say it? Um, hmm. Basically, we're continuing with where we left off, right? So we're introducing a new integration technique called U-substitution. And again, what I'll usually in class they wouldn't, like in your class they probably won't mention this, but I'll bring it up just for context. Remember, the key overall theme that we've been doing this week is that all the rules we're learning are the opposite of rules you should already know, right? If you're already comfortable on your derivative rules, then all of the rules that we've been talking about, for the most part, not 100%, but for the most part, are literally just the opposite of the rules that you already believe, because integrals are the opposite of derivatives. So that's like 85% of what we're doing here. This is also like that. So U-substitution, and again, I kind of hate this name, but U-substitution, when you're doing integrals, is the opposite of the chain rule. So it's the opposite of, or whoops, if I can spell substitution. Let's see. There you go. So it's really the opposite of the chain rule. So opposite of the chain rule. So remember what the chain rule allows us to do. If you have like the derivative, it basically allows us to take the derivative of what's called a composition of functions. What's a composition of functions? One function stuffed inside of another. So, and what the chain rule tells us is that it's the derivative of the outside, leave the inside, times the derivative of the inside. So that is what the chain rule says. Now, just to give an example, so you've probably dealt with many of these. I'll just give a quick example. But like if you have sine of x squared, well, we know how to take the derivative of sine of x, and we know how to take the derivative of x squared independently. But how do you take them when they're together? Well, you use the chain rule when one's inside of the other, to put it more clearly. X squared is the inner function. Sine of x is the outer function. This is a composition of functions. So you do the derivative of the outside, which is cosine, evaluated the inner function, not the derivative, but just the inner function, which is x squared. So just leave that. And then you take the derivative of the inner function, which is 2x. So 2x. So you get this as the answer. So again, that's like a typical chain rule problem. Now, U-substitution, again, I kind of hate the name because when you call it that, it's usually the way they explain it in class. It is not at all clear that it's the opposite of the chain rule, but it is. So what this process allows us to do, just to give an example, I won't go through a full one here, but basically it allows us to do this in reverse, right? So if you're taking the integral of like 2x times cosine of x squared, basically it would give you sine of x squared. Now, how does it do that? I haven't explained that yet. There's a systematic process you can go through to do it, and that's what we're going to talk about today. But I'll just say sine of x squared plus c, and you always need that plus c with integrals. So it's like if I was in charge of math, I wish I was. I'd be a good boss of math if anybody wanted to elect me to that. But anti-chain, or at least calculus, Calc AB and BC, I can handle. So like if I was in charge of math, I would cross this out of all textbooks and start calling it the anti-chain rule for here on out, because then it would be a lot clearer. It would be a lot more helpful. You'll see it later as we go through the process to actually do U-substitution, or what I like to call anti-chain rule. You'll see why calling it that is a good idea. I think it kind of helps you remember how to do it if you recognize that, oh, this is the opposite of the chain rule. So that's what we're going to talk about today. And this is a more complicated technique, by the way. This is like, depending on how you count, this is either the most complicated or the second most complicated technique that you learn in AB. In BC, there are many other ones that are more complicated than this. But I'm just putting into context. So it's like this is like a medium difficulty technique. It's like harder than what we've done so far. Like the other integrals we solved were a lot simpler than this by comparison. So this is going to get a little bit more involved as a technique. But let's go through this. So let's say I'm just going to copy this down, and I'll leave it like this. So let's walk through. We already know what the answer's got to be, right? Because you could literally just do the chain rule in reverse. But what I want to do here is I want to just show you the mechanics of U-substitution, and then we'll show a couple of problems, but I want to show you the mechanics of U-substitution, and then I want to show, or I guess, how should I word it? Basically the mechanics and how it actually, like how each step that we do here is actually behind the scenes undoing the chain rule, because I want to show you it's the opposite of the chain rule. So here's the idea. The first thing you do is you choose U, and then I'll just give you the simplest rules I can imagine. So there's a process to do that. So like how to choose U. So for U sub, when you're doing U sub, how to choose U, there's a systematic process. That's the good news. And you just do that every time. So step one is choose U equals the inner function. So if there's clearly one function that's inside of another one, that's U. Step number two, if that fails, or like they could either fail, and we'll show how it would look if it fails, but that could fail, or if we do or if there is no inner function, that's another possibility, I'll say. Then you just say U equals the entire denominator. And then try other things, basically. So these two, so just to be clear, this first rule will work like if you're in a typical class, it will work 85% of the time. This rule will work 10% of the time. So if you just remember the first two, that'll handle 95% of U sub problems that you're likely to see. This one's harder. There's a lot of other tinier techniques. You basically just try different stuff to see what works with this one. So there's like many other rules, but they're a lot rarer, basically. So that's the good news. So that's how you choose U. So here, let's start with rule number one. Again, remember, 85% of the time, all you need is rule number one. If you just do that, it'll work. So what's the inner function? What function do we have that is clearly inside of another? Hopefully you can tell right there. So here it makes sense to say U is x squared. Okay, so we've done that. Now what do we do? After you choose U, that's the hardest part, by the way, of U sub. If you choose U correctly, everything else will fall into place. If you don't choose U correctly, everything else will not fall into place, and you'll hit a dead end, and you'll get stuck, and you'll waste a lot of time on your test, which is bad news. So what you want to do after you've done that, take the derivative, so du dx, and you want to use this notation. You don't want to do the U prime. You'll see why we say that in a second. You want to use what's called Leibniz notation. So that's good. And then looking at this, what's the derivative of that? 2x. So that's good. Now, once you have this, here's the next question to ask. You don't have to ask this question. You could just start doing the work we'll show below, but I think it's a good idea to do it. So it's like, how to tell if U is right? So remember, this is step one is choose U. Then we take the derivative, and now how can we use the derivative to tell if it's going to work? The idea is before dumping in effort, right? Because like this is another point I want to make. Everything we've done so far with integrals and just calculus in general, and also math in general before calculus, literally everything you've been doing in your math class the last 5 years has been what I would call deterministic. What do I mean by that? I mean that if you know the trick, if you know how to do the problem, you will get it right. End of story. This on the first try, by the way. So it's like you do the rules they tell you, it will work 100% of the time. If you make a mistake on the rules, then you might get it wrong. But if you do the rules they say correctly, you will get it right on your first try. This is the first time in calculus where that is, or in math in general, where that's not true. It is actually not true anymore that if you follow the rules, you will get it right on the first try. What can happen is you try this U sub and it fails. And then you go on to the next one. Maybe that fails. That happens sometimes. Like maybe it fails twice in a row. And then on the third try, you pick the right U. you could do everything right. But and still fail, I guess is the point. Why is that? Because these problems are so complicated, especially with integrals in general. You have to get the patterns to match up perfectly, and there's so many patterns that it's hard to do that. So you basically have two options. You could remember like 200 different patterns, and if you remembered all those 200 patterns, which is kind of the point, like I've been tutoring calculus for many years, so I'm at that point where I can just tell what the answer is right away most of the time. But even I'm not like there perfectly. But you would get there if you did calculus for years and years. You would like internalize, just as you see more stuff, you would internalize more patterns naturally. That's one option. And so I don't really need to follow these rules. I can usually just jump right to the right answer. I can tell because I've seen it before. But if you don't want to remember those 200 like subtle patterns, then the good news is you can just remember three patterns, roughly, basically three rules. The downside is you might need to try two or three of them on some problems. So that's the trade-off. It's pretty efficient, like compared to the alternative, right? Like I think remembering these rules is a lot better than obviously just doing years worth of U-sub problems until you've internalized all the possible patterns they can throw at you. And it's just that's the price we pay. Like because we're trying to like generalize a lot of subtle patterns with three simple rules, they're going to be overly simplified or overly simplistic. So we're going to get it wrong a part of the time. And this is going to happen with later integration techniques too, by the way. This is going to happen with integration by parts as well. But the key idea, I guess, you just have to get used to this idea. You have to get used to the idea of failing, which a lot of students don't like, but you need to learn to like it in order to make the most progress. The important thing is that we fail fast. So that's one thing I want to emphasize. You will choose the wrong U sometimes, and it's kind of an unfortunate idea. It's kind of like the real world, honestly. It's like you could work really hard, but if you have a bad strategy that doesn't work, you're destined to fail no matter how hard you work. That's kind of the cold hard truth. Um, so that's not good, right? To hear that, and it's kind of a tough idea for students to accept, but it will happen. So you have to accept it. So there's no real way around it. The only way around it is to internalize those hundreds of patterns, but that's like a cure worse than the disease. It's like it's more effort to do that than just fail every so often. So it's not a big deal if you fail, as long as you fail fast. So that's kind of the key point I want to get by. That's what this box is for. So you could like dump 30 more seconds of work into this problem, and then like maybe 20 seconds from now, 20, 30 seconds from now, we've already dumped like 5 seconds in. Once you've internalized, I know I've spent much longer explaining it, but once you've internalized these rules, like this would take you 5 seconds. Hopefully it's clear to see that, like as long as you're good with your derivative rules and all your fundamentals, you've put in 5 seconds of work right now. What you could do is you could put in 20 more seconds of work and then hit the dead end. What this box, that's what happens if you don't use what I'm about to write in this box. But if you use what's in this box, then you get to save those 20 seconds. So instead of dumping in 25 seconds to a problem, to one choice of U before you realize it's going to fail, and then you try the next one, you just dump 5 seconds in, and you already know it's very unlikely to work. It's a lot more efficient. So you want to prevent dumping in a lot of effort to something because now it's like we have to play the odds, right? These are no longer deterministic. It's like you can follow the optimal strategy and still lose, at least like for the first guess or two. So there's a bit of there's a little bit more chance involved, I guess. So we got to play the odds intelligently, and the best way to play the odds is don't dump a ton of effort because that's the worst thing you can do, by the way, is dump in a lot of effort to something that won't work. If you make the wrong choice of U, it doesn't matter how much work you put into it, it can't work. It will fail. So you need to cut your losses quickly. You need to learn that you need to realize it's gonna fail as fast as possible, and then cut your losses. That's the key. The worst thing that can happen is you put a lot of effort into something that doesn't work anyway. That wasn't going to work anyway. If it's not going to work, you just like learn that quickly and just on to the next one. And as long as you can do that, like maybe you spend 5 seconds, maybe you spend another 3 seconds on the problem, just checking what's in this box instead of like actually going through the work of like setting up the integral and all that stuff below and doing the substitution. And by doing that, you just bought yourself, if it fails, 20-ish seconds. And those seconds stack up on a lot of these problems. So that's why we have this. That's why we want to tell before dumping in effort. But how do we actually do it? So if we're multiplying by something proportional to du dx on the outside, it will 100% work. 100%. Guaranteed. If we're not, 95% chance it won't work. But it could. So I wish the rules were better than that. I wish you could be certain it will work, it will not work. Unfortunately, there are some weird scenarios where even if this check fails, it still works, but they're very rare. So these are the best rules I can give you that are right 100, that are actually realistic 100% of the time. I wish it were simpler than this, but it's not. So now what do I mean? But this is still valuable if you think about it, because you can at least, by just like quickly checking, you can be 100% sure. Like if it's going to work, you can be 100% sure about it in this case before dumping an effort. So at least like this will help like the majority of the time, right? Because like half the time you expect it, like about half the time, or most of the time you expect it to work, in which case you just confirm it works before dumping an effort. Whereas sometimes when this rule fails, but it's like, and it fails anyway, it still fails. Like when you hit this rule, it'll fail the vast majority of the time, 95%, but sometimes it'll still work. That's really the problem. That sometimes where it still works and the rule says that you don't, you kind of have to ignore the rule in that case. But it does happen, but it's very rare. You will see them, to be clear, but it's like it'll be very, very, very few of the problems that you see. So hopefully that makes sense. This is the strategy of U-sub. If you get these, you're good. So now let's take a look at this. So if we're multiplying by something proportional to du dx on the outside, it will 100% work. So here, now to be clear, we have our u, which is our inner function, and then we have an outer function outside of that, right? So here's like cosine is the outer function. We're talking about multiplying by something different that's not like, we're not saying the outer function. So it's like this is separate than that. But something that we're multiplying by on the outside of the outer function. So like in this problem, it would be the 2x. So here's the magic question. Is 2x proportional to du dx? Like, in other words, could you just take du dx and multiply by some constant to make it be that? That's the real question. That's what we mean by proportional. And the answer is yes. Not only is it proportional, it is literally equal. The proportionality constant is 1. If I just multiply that by 1, there you go, that's 2x. So yes. So that means we're in this case. So this is like the simplest that U-sub is going to get. It's like your first guess works, and you know it's going to work before dumping an effort. And then it's just you do the work, and you know you're not wasting effort. It's not wasted effort as long as you know that it will work by the end of it. If you don't know that the process will work by the end, then it might be a waste, and that's when it gets riskier. That's the worst thing you can do, is waste time on a test. That's the thing that'll bite you. If you fail 5 times, it doesn't really matter as long as you realize it within 5 seconds. You've only lost 25 seconds. But if you spend like 30 seconds or a minute on each problem, now you lost 5 minutes. That is costly now. That's the real cost, is wasting too much time on a bad strategy. So with that, we know it's going to work. And now here's the work that we do. What I like to do is I like to isolate dx. And I recommend doing this. This makes everything easier. So we're going to write 2x dx. And then basically just do du over 2. So basically just replace whatever's on the right with dx. That's algebraically what happens. That's good. Now, once we've set all that up, that's all of our setup. Now we can actually do the substitution. So the thing you circled, and I do recommend, this sounds like a tiny thing, but I do recommend circling u. I think it makes things easier. You like whatever you circled, you replace that with u, leave that. So leave the 2x there. So leave the 2x. So let me do this. Leave the 2x times cosine, replace that with u. So cosine of u. And then replace the dx with what's over here, which will be du over 2x. And then if you think about this, you can simplify this down a bit. So it'll be integral, and then hopefully it's clear, 2x. Like this is just the whole thing. This is a bunch of stuff multiplied together. So I can like pull the 2x right here, and those, you can see those cancel out. And then we're just left with cosine of u du. Now, once you get to this point, like I said, I kind of already crossed it out, so we know it's going to be good. But once you get to this point, this is a problem. You cannot have 2 variables in the substitution. You have to have only 1 variable. So, like specifically, we had a function in terms of x, and we're trying to transform it to be a function in terms of u. You'll see why in a second. It's really to make it simpler so we can actually solve it. But so here, like the x's better cancel out. The 2's don't necessarily have to cancel out. We can deal with the constant. Here they do cancel out, but like the x's have to cancel out. If the x's don't cancel out, like if this is x squared, you're stuck, most likely. Maybe there's a clever trick you can pull out of your hat, hopefully, but odds are you can't really solve it. The x's need to cancel out 95% of the time. There's 5% of the time where you can kind of finagle your way to the right answer, I'll say. But like the vast majority of the time, you expect those to cancel out. And now this is completely doable. Now we just have to say, what's the integral of cosine of u du? Well, we talked about that the other day, right? We talked about how to take the integral of trig functions. Hopefully you remember this one's sine of u plus c. Now, all we have to do at the end, remember u was really just a means to an end to this problem. We don't really care about it. What we really care about is x. So we need to, whatever we chose for u, we need to substitute that back in. So if u equals x squared, we now need to substitute that back in. So sine of x squared plus c, and that's our answer. Just like we knew, right? We already knew that was the answer, but hopefully you can see that that's the process. So the thing I want to talk about here, let me just pull down the key insight, by the way. Remember, this is the opposite of the chain. You don't have to worry about it. If you just do these steps, if you just choose a u according to these rules, and you take the derivative and you isolate dx, and then you plug them in and try to simplify and solve like we did, that's U-substitution. We just did that technique. You don't really need to worry about much beyond that, but just to point it out, these rules that we just followed are systematically designed. They're designed to systematically undo the chain rule. So, for example, the spot here, you see where the 2x and the 2x are canceling after we like cleverly substitute in dx. That is basically the thing that makes this part disappear, right? Because if we're starting with this and we want to end up with this, we need to make that disappear. That, like when we cross out the 2x's, that's what happened. And then the g on the inside, the g, think of the g as u. So remember how we had like a u? It's like we had cosine, we had a function of u, cosine of u. U is the inner function. So like the u and U-substitution is like the g from the chain rule that you've used before. And now what do we have? We have f prime of u. Well, now what do you do to undo that? Well, you just integrate f prime and you get f. And next thing you know, you have like just f of u or f of g. So hopefully you can kind of see there. It's a little weird, but we're like the process we did below systematically undoes the chain rule. You don't have to worry about it. It just does that behind the scenes. So that's good. So hopefully that makes sense. That's like your first U-sub problem. Now let's do some others. So I'm just going to pull these down and then we'll take a look. So here, this happens like, yeah, let me do a tweak here. Let's say we're doing, I'm just going to make up x squared times square root of x cubed plus 1 dx. So here, let's use the rules again. So what should u equal? U should be the inner function. Is there any function here that's clearly inside of another? Yes, actually. X cubed plus 1 that makes sense to call u because it's inside of another function, the square root of x. So that's u. At least that's our first guess. And remember, this first guess works 85% of the time. This works 10% of the time when the first one fails. And then 5% of the time it gets more complex. But the simple rules handle the vast majority of your problems. These come up infrequently, but they do come up. What's the derivative here? 3x squared. And now we ask the magic question. Are we multiplying by something proportional to the derivative of u on the outside? Not the outer function, right? The square root, but like outside of that. And the answer is yes. X squared is proportional to 3x squared. Why? Because if I just multiply 1/3, if you can multiply a constant by the derivative and make it equal this, they are proportional. So it works. So we know. So again, this is more good news. We're 100% sure. Our first guess worked. We're 100% sure that it's going to work. Now we dump in some more effort. Now that we know for sure it's going to work, 3x squared equals dx. And then let's try substituting this stuff in. So leave that square root of u, right? The thing circled gets replaced with u, and then dx gets replaced with this thing, du 3x squared. And then we simplify. So, and you can see here, this like the x squareds cancel out now. So that works. We're going to get stuck with the 1/3, but that's not a problem because we can factor that out, right? Division by 3, we can pull that out, no problem. And then we'll have square root of u du. Now, once we get here, this is pretty easy to solve if you know the power rule. I don't think we've talked about it before in these videos, but like this is like a relative. All you have to do really is use fractional exponents to convert it. So 1/3 integral u to the 1/2 du, and now you can just use the anti-power rule that we talked about before a couple days ago. I think I recorded a live for that. So here you just add 1 to this and then divide by it. So 1/2 plus 1 is 3/2. So u to the 3/2, and then divide by 3/2. So 1/3 is really 2/3. You just take the reciprocal. So you have 1/3 on the outside, and that'll be 2/3 plus c. And then what was u? It was x cubed plus 1. So long story short, hopefully it's clear, this thing will be 2/9 times the, well, I'll just say it like this, x cubed plus 1 to the 3/2 power plus c. And if you really want to continue, what does the 3/2 power mean? It basically means square root it. That's what the 1/2 power means. And then the to the third power means cube it. So 2/9 square root x cubed plus 1, the whole thing to the third power plus c. That should be our answer. And by the way, to check that that's the answer, how would we think about how would we check? How would we check that that's the answer? Basically, remember, if we're saying that this is really the integral of that, then the derivative of this should be that. So let's try that. Like, and again, you'll use the chain rule here. So 2/9 times, I'll just convert it back, x cubed plus 1 to the 3/2 plus c. I'm going to go through this a little more quickly, but hopefully it's clear. You bring down the 3/2, so you're going to get 1/3 on the outside, 1/3 x cubed plus 1 to the 1/2, right? So like bring the 3/2 in front, subtract by 1. That's the normal power rule. But according to the chain rule, that's just the derivative of the outer function, leaving the inner function. Now we need to take the derivative of the inner function, 3x squared. The 3 and the 1/3 cancel out. You get what we started with. Hopefully that's clear. X squared square root. So that checked out. So there you go. Another problem solved with U-sub. Now here, let me grab another. I just want to show a couple examples just so you're familiar with it. So yeah, so just a couple examples. Let's do, let's see, what should we do here? Let's say, trying to think. Let's say 2x, let's say 3x over x squared plus 4. How about that? Now, when you look at this, let's try this. This is solvable by u-sub, I'll say. So u is equal to the inner function. Well, there is no inner function. Now, the good news is that's not actually bad. That's fine. Because like it would actually be worse if we had an inner function and it didn't work. You know what I mean? Because then we would have to dump in effort to checking it and trying it, etc. That would be worse. Here, there is no inner function at all. So this rule takes you 2 seconds, like one or 2 seconds to realize it's not going to work. You only waste 1 or 2 seconds. Not a big deal. That's fine. We can do that. Here, u is equal to the entire denominator. We do have a denominator here. The keyword is entire. Don't just say x squared, do x squared plus 4. So if u is x squared plus 4, then what's du dx? 2x. And then remember, I like to circle that. So here's the magic question. Are we multiplying by something proportional to the derivative of u? We are, but it might not be obvious in its current format. Try this. Whenever you have like a denominator, take the numerator and just multiply it on the outside like this. Now, is it clear that like when you look at it like the numerator is the multiplication, I guess is my point. And yes, 3x is proportional to 2x. If I multiply by 3/2, that would equal 3x. So there you go. So this is going to work. So now we know the u-sub is going to work for sure. So like the second rule worked this time, and then we're for sure that it's going to work. And then here, how do you do it? Let's make the substitution. I'll put it back in the form that it originally was, but 3x over u, and then the dx. Again, you can kind of see how this is going to go. Dx is going to equal du over 2x. If I substitute that in, du over 2x, then the x's cancel out. What do we get? 3/2. So 3/2 integral 1 over u du. And we get what? 3/2 natural log of u plus c. What's u? X squared plus 4. So 3/2 natural log of x squared plus 4. plus C on the outside. That's the answer, and you can check that one. That'll work. So that's another U-sub problem where we actually have to use the second rule, and then I'll show one more here. So here, this is actually kind of interesting, or the next one that I had in mind. Remember, what did we start with? We started with 2x times cosine of x squared. Let's just not have the 2x on the outside. Like, instead of having 2x cosine of x squared, I'm just going to have only the x squared, so not the 2x. And this is kind of a good lesson in general. So here, what's the choice of u? The clear inner function, u equals x squared. Derivative is 2x. Are we multiplying by something proportional to the derivative of x squared? No, we're not. You can imagine there being a 1 there. So like if this was just a constant, that would be fine. But we don't have an x on the outside. That's a problem. That means we're actually in this scenario. There's a 95% chance this won't work, this U-sub. And actually, I'll say I know for a fact that there's a 100% chance this won't work. We're going to get stuck when we try. So let's watch what happens, just so you can see what it looks like to hit a dead end, so you're aware of it. Cosine of u, and then dx, again, dx be du over 2x, so du over 2x. Uh-oh, now we're kind of like this x doesn't cancel out with another x. That's the problem now. So we're going to have, like, what are we going to have? We're going to have, like, the 1/2 is fine. That's not a problem. The 1 over x is the problem. We're stuck. So, yeah, we're stuck. Now, what you can do, potentially, and this is where I kind of say this is the 95% of the time. 5% of the time, what you can do is you always use your original choice of u, and you say, what do I have in here? X. Is there any way I can rearrange this to get that? You just square root both sides. X is equal to the square root of u, and you could say 1 over the square root. You basically, hopefully it's clear, you can turn this problem into cosine of u over the square root of u. But the problem is we don't know how to solve this either. Like that, the division, like, so you can rearrange it, but it's like we basically hit a dead end. There's another way U-sub doesn't work here. It doesn't, like, you cannot solve this integral with U-substitution. You actually need to use trig identities. There's actually a clever idea called the power reduction identities from trigonometry. That's how you actually have to solve this thing. You can't solve it with U-substitution, at least not right off the bat. So this is what a dead end looks like. But I guess here's my point. Think about that work we did. We found the derivative, then we plugged in, then we realized we got stuck, and then we tried to finagle our way out of it. We wasted like 15 or 20 seconds there for something that only had a 5% chance of working. That's not a good trade. Sometimes it does. That's the problem. I wish I could say 100% of the time it's not going to work. But the truth is it does work sometimes. That's where it gets a little tricky. But 95% of the time, you should stop dumping in effort when you end up in this step. If you've exhausted all other possibilities and you can already tell like there's nothing else to force it to work, and you're like really sure U-sub's the right option, maybe try to put in this extra effort to force it to work. That does work 5% of the time, but most of the time it doesn't work. So there you go. Yeah, this is like, again, this is not everything you'll need for U-sub. You got to practice. There's a lot more to practice, of course, but this is the 80-20 of it, right? If you can do this, that's 80% of your problems. Like this is the 80-20, I'll say, of U-substitution. And this is, again, you can see the rules are getting more complicated. It's like we took a whole video just to explain one rule, because it's more than a rule, really. It's like a whole technique that has its own strategy and all that. But this is how we do the opposite of the chain rule. So I hope that makes sense. Everybody, if you have any questions, like I said, always feel free to drop them in the chat or just post in Skool, and I'll record a video answering any questions you have. Other than that, hope that was helpful for everybody. I hope U-substitution makes a lot more sense now. The good news, the key point I want to get across is there is, like, even though it's not deterministic, there's a bit of probability involved, like with how you choose. There is an optimal strategy, and it's like you can remember you can and should remember the optimal strategy and then do it. That's the good news. So it's like a lot of students think that U-sub is like kind of like 80% art, so to speak, where you just kind of have to get a feel for it. It's not. It's like 85% science, like 15% art. So it's like there is a little bit of like get like feeling it out to that you'll develop a good feel for it as you do more problems. But but like 85% of it is a science, I would say. So there you go. Hopefully that makes sense. If you have any questions, let me know. Otherwise, I will see you guys in school. Have a good weekend.